Welcome back. In our last meeting, we talked about potential energy, energy stored inside an object. And along the way, we kind of broached the idea of how work factored into it. Now, 2 days ago, we showed or talked about how work done in an object equals the change in kinetic energy. And then we talked yesterday about how work done in an object equals the change in potential energy. And we talked about the confusion there a little bit, but how in reality, it really just depends on what we're going to try and do. Well, what this does is now leads us to possibly the most important law in all of physics. In fact, in all of sciences, because this is a law that transcends physics. It goes into chemistry, it goes into biology, it goes into all aspects of the sciences, and that is the law of the conservation of energy. Okay? So energy we know is defined as the ability to do work. We've talked about that. So we kind of let off of that before. I'm going to read it here, that the work done is always equal to the change in the energy of an object. And we measure the amount of work done, we measure the amount of energy an object has by how much work is done on it. Okay, so consequently, work and energy still have the same units. We should have noticed that from before. Units for kinetic energy, joules. Units for potential energy, joules. Units for work are joules. And again, it's very key that to make this true, whether it's work done equals the change in kinetic energy, or if the work done is equal to change in potential energy, or if the work done is equal to combination of both, depends on the type of work we do on it. But like I said, this leads us into possibly the most important law in all the sciences, and that is the law of conservation of energy. And I'm going to write this out because I didn't put it in the notes because I wanted this to be something that you write out. And that is that the total amount, and I'm going to put it right here, the total amount of energy in any process is constant. Now, I will say that this is a simplified version. For those of you that ever think about, or those of you that come and visit me and take AP, or for those of you who go take a college physics level class above this one, you're going to find out there's some tweaking here. This is an oversimplified version, but it basically is that when the total amount of energy, we have a certain amount of energy, this energy can change forms. It can go from potential to kinetic, and potential gravitation, potential elastic. It can change forms, but the total amount of energy in any process, in any situation, will always stay constant. That's our oversimplified version. So one key thing to know here, and I'm going to highlight it, when work is done on an object, that energy of the object changes, okay? Not the total energy, just the type of energy. So work changes the type of energy. And let me give you an example. If I take and I have a ball in my hand and I want to throw, say baseball, football, soccer, whatever, and I have a ball and its initial velocity is 0, I do work on it, boom, and that's going to cause that ball to have an increase in the kinetic energy. You're going to say, well, wait a minute. The law of conservation of energy isn't true because its energy was 0 and now it's something. But if you take a look, that energy came from me. I did work on it. I took energy from my body, chemical energy stored in my body, and I put it into the ball. The work is what transferred or transformed that energy from one part or one type to another. If I take this pen, sorry, let me bring it down on the screen. Right now, it has gravitational potential energy. If I drop it, it loses gravitational potential energy. Like, well, hey, the law of conservation of energy stays has to be the same. But in the process of it falling, gravity does work on it. And when gravity does work, it's transforming that potential energy ahead here into kinetic as it falls. And so work transforms or transfers. And actually, I'm going to add that on here. Let me bring this up. Work changes type of energy. I think a better way of putting it, that work transfers or transforms energy. And that's why it was so important. We said that the work done equaled the change in energy. Maybe the change in type, maybe from one object to another. But that work transfers or transforms, that's what I saw there, energy. Okay? Now, we're going to simplify. Like we said, we've already simplified the law of conservation of energy, saying the total amount of energy is constant. We can simplify it even more if we ignore air friction and if we only look at the transformation of energy from potential to kinetic and vice versa. And so if you ignore air friction and you only look at potential to kinetic, we can rewrite our law of conservation of energy. By the way, you'll see me write this as loco E, law of conservation of energy. And in the simplest case, we can say that the potential energy initial plus the kinetic energy initial must equal the potential energy final plus the kinetic energy final. They must be equal. You'll also see me write loco E as E topped initial must equal E topped final. Or one other way of doing it, and I want to introduce you to this term. I can use this symbol and what that symbol means, it's the Greek letter sigma. It stands for summation. So if I add up all of my initial energies and I add up all of my final energies, they must be equal to each other. Okay? Now again, highlight, mechanical energy is conserved only in the absence of friction, which again, because we always deal with the simplest case first and work our way to the more complex, this is what we're going to deal with a lot. We're going to ignore air friction. We're going to ignore friction on the ground. We will bring it back in from time to time, and when we get to the heavier duty problems, we'll bring it back. But if all we're going to do is ignore air friction or ignore friction, we can write this. And tomorrow, we're going to do a bunch of problems with this law of conservation of energy, and we'll build off of loco E. I will teach you how to build these formulas. Because if you start with sigma EI and sigma EF, if you always start here, you can never go wrong. Our last tidbit is the one time that energy, the law of conservation of energy, kind of falls apart. Guy by the name of Einstein, may have heard of him, only came up with the most famous physics equation ever. And he discovered or theorized that energy and mass could be converted back and forth. That energy can become mass and mass can become energy. We're going to just discuss that a lot more when we get to nuclear and subatomic physics. We'll talk about that a bunch more. This will not factor into our everyday lives. This will not factor into our everyday problems here in this class. Okay, so you don't have to worry about, oh, I dropped it. Well, how much mass did it gain? Not going to happen. You don't have to worry about that part. But just for reference, this E, again, stands for energy. And that's going to be measured in joules. M is my mass, measured in kilograms. And C, this is a constant. This is the speed of light, which you can find on the front page of your references. I'm going to give it to you, but just know that you don't have to memorize it. It's on the front page of your references. 3 times 10 to the 8th meters per second squared. And so if we start talking about how mass can be converted over and energy, then we have to include that in. And so we can rewrite our law of conservation of energy to be the conservation of mass energy, which is that the total amount of mass and energy in any process remains constant. Okay? And so you won't hear me use this often. We won't use it often until we get into nuclear and subatomic. For our base problem, if I'm just going to drop a pen and ask you law of conservation of energy with it, okay, or take one of the little pop-up spring pop-up toys and ask you to analyze that, there's not going to be a change in mass, and so you don't have to worry about it. So we're going to end chapter 5 on that. We'll do a lot more practice with it tomorrow, but we'll go from there. So everybody have a great night. We'll see you later. Bye.